Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today we have the paper ICON, Implicit Clothed Human Obtained from Normals. And I'm happy to host Yuliang Xiu. Hello, Yuliang, and welcome to the podcast.
Hello, it's Zeke, and I'm very happy to be invited to talk about our recent paper.
So this paper was accepted to CVPR 2022. So it's hot off the press, very fresh, very new. The actual print version, camera-ready version wasn't even submitted yet. Can you introduce yourself?
My name is Yuliang Xiu, and for now, I'm a second-year PhD student at SMPL Institute for Intelligent Systems. And my advisor is Michael J. Black. And before I moved to Tübingen, I was a PhD student at the University of Southern California, working with Hao Li. And for now, my research interest mainly lies in the 3D human digitalization, and including but not limited to reconstruction and modeling, animation, etc.
Yeah. And who are the co-authors of this paper?
Oh, there are 4 authors, and I'm the first author, and the second author is Jinlong Yang, and third author is Dimitrios, and both Jinlong and Dimitrios are the postdocs in our group, and the last author is my advisor, Michael J. Black.
In a TLDR kind of format, let's dive into the abstract. What is this paper about?
The main focus of this paper is to reconstruct the 3D clothed humans from the molecular input. The molecular input means the colored image or the videos.
You have an RGB image of a human, and you want to reconstruct that human with his clothes on.
Yeah, and with all the details like the clothes wrinkles and the haircuts, and with the help of the implicit functions, which are a very hot topic in the computer vision community during these years.
Right. So why is this an important problem? Like, where can you use this?
It's a research both in the industry and academia. Like in industry, there's a long way to explore how to reconstruct the humans from the wild inputs, and like the molecular videos. There's an application which name is teleportation. People want to teleport the 3D clothed humans from one place to another place. So the reconstruction is the first step. And for the academia, a main focus of my advisor is to understand the whole world from the video or from the image. So how to reconstruct the humans in great details is an important step to understand this world or understand the videos on the internet.
What are the main challenges when tackling this type of problem?
Before the ICON, there are several papers focused on this topic. I think you must know the PyFu HD. And also before PyFu HD, there's PyFu and Pamia. All such kind of works are working on to reconstruct detailed clothed humans from the image. But most of them cannot generalize well on challenging poses because the training datasets are mainly the standing pose or the fashion pose. So the model trained on this kind of dataset cannot generalize well on the unseen pose like dance or the sports or the parkour. That's the problem. And this is also what the ICON focus on.
Mm-hmm. So what you're saying is where most existing methods fail or struggle is to generalize to these kind of extreme extended poses. And your method is right there to address this specific problem.
Yeah. And also, there's a very intuitive solution, which is we can increase the data set. Like we can buy a more high quality render people scans for the training with all kinds of poses. But there's 2 limitations. First one is the render people is very expensive. Like I think it's 80 euros for one rigid person. So it's very expensive. And on the other hand, the number of the commercial 3D humans are still limited. And for some motions like the parkour or the sports, they are very hard to capture because the motion is very fast. You cannot capture with some 4D scanners. So even though we can buy more data set, we're still thinking about how to improve the robustness by changing the framework instead of using more data.
Like every problem in our deep learning world, right? You throw more data at the problem, it should be able to generalize better. But in this case, it's really hard and really expensive to get that data into an actual system, or just to capture that high quality data that you need for training.
Yeah.
So let's talk more about the related work. So before anybody wants to read your paper, which papers would you suggest them to read, and what are they about?
In this field, using implicit functions to do the human reconstruction, I think the first paper is PyFu, of course. PyFu is the first one to introduce implicit functions in closed human reconstructions. And then the first author of PyFu, Shrinsky, has the second paper, which name is PyFu HD. The main focus of PyFu HD is to improve the details by using the 4K image, and with the help of the normal image, the normal prediction, with the help of normal prediction. And then actually at that time, the people already realized that the PyFu is not robust to any pose. So they are thinking about maybe we can introduce some geometry prior into this problem. Like we can using the SMPL, the simple into the whole framework. So the Pamia and S3 and also the GeoPyFu were trying to introduce the geometry prior into this problem. I tried some, I tried the Pamia on the very challenging pose, and I give Pamia the accurate simple body mesh, but it still cannot generalize well on the unseen pose. And I think the main reason is all these previous works use global encoders. They use global encoders to encode the features from the image, to encode the global feature from the 3D voxels, but all of them use these global encoders. But global encoders, to make the global encoder really can generalize well on the unseen pose, you training it on a large scale dataset. So the main contribution of Icon is just remove the global encoder. Just forget about the global encoder. We just use local features to solve this problem, and that's doable, and that's the key insight of Icon.
Mm-hmm. So now let's dive into the approach. So how do you do it?
There are two main modules in Icon. The first one is we want to get a very detailed and correct normal image from the input RGB image. This is the first module, and the second module is with this detailed closed image, and also with the simple body mesh, we use their local features to regress the implicit surface. And finally, use a machine cube to get the final mesh from the implicit field. That's all.
Okay, that was too fast even for me. Let's try that again. You get an input RGB image, right?
Yeah, we have an RGB image, and we try to predict the normal image from this RGB image.
Right. So that's where it kind of splits into two, right? You get a normal image for both the front and back kind of views, right?
Yeah. And there's one thing. In the PyFu HD, they also predict the front and the back normal image. But the input of PyFu HD is only the RGB image. But for Icon, we also render the front and back normal image from the simple body. So we concate the body normal image and the RGB image together and try to predict the closed normal image. And the reason why we use this body normal image is because the simple body already provide many geometry informations about how the human look like, how the human shapes the pose. And so we think with this geometry prior, the normal prediction will be more robust. And we do some experiments in this paper, and our conclusion is yes, this geometry prior makes sense.
Okay, so you have your RGB images input. You first get this kind of the pose estimate from like the simple pose estimate, right?
Yeah.
Then you get like these two normal estimates from the simple code for both the front and back without the close, right? Because the simple doesn't have the close.
Yes.
Then you have like this building block architecture that you use to to go from this normals from the simple model into the closed normal predictions, right?
Yeah. And then for every point in the 3D space, we just query the normal vector and the SDF of a body mesh, and use these features for the implicit regression.
Right. Okay. So you take those normals that you have, now you start throwing points in 3D space, and you train an implicit function, implicit model as a neural network, of course, to get this final. It's not a sign distance in this case, right? It's an indicator function, like it's an occupancy grid, right?
The final output is not SDF; it's still an indicator function, and but we use the SDF computed from the simple body, and for every point, let me explain this way. For every point in the 3D space, we firstly use this 3D point to query the closed normal vector, and to query the body normal vector, and to query the SDF value defined on the simple body. And then we have 7 dimension of the features. We just use these 7 dimension features to regress the implicit surface.
Okay, so using all of the information that you gather along the way, both the simple body normal, closed normal, and SDF from the simple model.
Body.
So simple body. And then you use an implicit function to regress, and you get an indicator function, which you then can feed into like a marching cube algorithm to get the reconstructed mesh.
Yeah, exactly.
Okay, there is a point about visible points and invisible, like front and back points that you, like this kind of trick that you do there, right?
For the closed normal image and the body normal image, we also have the front and the back, right? So in icon, for every point in the 3D space, we just calculate the visibilities according to the camera position. And then for the visible points, we use the front normal. For the invisible points, we use the back normal.
Mm-hmm. This is kind of a way of making it consistent, right? Because normals there's like the ambiguity problem with normal directions. So this is why it's important to know if the point is on the front or the back. So you get consistent normals all over.
Yeah.
Interesting. A lot of details. So let me recap again, just to make sure that I got it right this time. Okay. You get an input RGB image. You get the simple pose body shape estimate, right? Then you can have like front and back normal image based on this simple body. Then you feed those normals into 2 networks, right? One for the front, one for the back, to get an estimate for the closed normals. Then you query every point in 3D space and try to figure out if it's in the front or the back, like if you see it or not. So then you have 7-dimensional vector that you use to train the network, which includes the SDF value, the 3 normal components for the simple body, and then another 3 normal components for the clothed body.
Yeah.
Right? And how do you train this? So what is the loss for the regression?
The loss is just the same as all the previous works. Just L1 to regress the occupancy value 0 or 1. Inside is 1 and outside is 0. It's just a L1 loss. Yeah.
Okay, so just an L1 loss on the occupancy to train all of this.
Yeah.
Okay, but there are additional losses, right? There's like a VGG loss and a pixel loss, and
we also use the VGG loss and the L1 loss for to train the normal network. The networks which used to predict the closed normal image from the body normal image.
Right. Is this trained separately or end to end?
That's separately.
Okay, so you first train the closed normal prediction component. Once you have that, you freeze that, and then you train the occupancy one with the occupancy loss that we just mentioned.
Exactly. I think there's a very important component, because we use some off-the-shelf post-estimation to estimate the simple body, right? But there's no guarantee that this estimate post is correct. So we just propose a new feedback loop, which you can use to optimize the simple body and the closed normal iteratively, which means the closed normal image can be used to optimize the pose parameters. And with the refined pose parameters, we have a better body mesh, and this better body mesh will in turn improve the closed normal image. So that's a feedback loop.
So you first get the estimate for the body pose, right? But maybe that's incorrect. You compute the clothed body normals, just like we said before, but then you use those to see if they match the body one, right? So if they don't match well, you optimize the body based on the normals.
Yeah.
Right? And then you do that iteratively. How many iterations do you do in this optimization? Is this like a long one, or like a few iterations and you kind of just fine tune it?
In my experiment, I just use 50 iterations. Mm-hmm. And also, if you use more iterations, like 100 or 200, of course, you can get a better final reconstruction results, but it will take longer time.
And this feedback loop you do after you trained everything, right?
Yes, it's only used during the testing.
So that component is only during testing. Okay, yeah, that's an interesting idea, right? So because you're using an off-the-shelf pose estimator, it doesn't guarantee to give a good estimate. So you're actually using the closed normal prediction network that you have that works well to adjust the body pose and get an overall better performance.
Actually, I tried several pose estimation methods like the pair, the PyMath, and the Pixie. They all have their advantage. Like the Pixie is good for the hands and the expression, and the pair has the better performance on the occlusion cases. Mm-hmm. And but PyMath is pretty stable, but none of them can satisfy all the cases. In my release code, I provide all them three. So if you like, if you test your image on the PyMath and it does not work very well, you can just change it to the Pixie and to see what will happen.
It happens a lot, right? Every method has its own benefits, and you sometimes need to pick and choose which one you use depending on the application or the specific image or problem that you're working on.
Yeah.
Okay, so let's move on to the experiment section. So how do you even evaluate this task?
First of all, I think I need to first talk about the how the PyFu or the previous works do these evaluations. Most of them do the evaluations on the render people dataset and also the buff dataset. The buff is with the dynamic 3D closed humans. But there's one limitation, which is the buff is not a very big dataset, and the motions are quite limited. And also the render people, they only use 50 render people scans for the testing. But we want to prove that icon is more robust to the unseen poses. So I just use another dataset, which name is CAPE, CAPE. And CAPE dataset is bigger than the buff with more motions, and some of them are very challenging. So I just split the CAPE dataset into two parts. One part is with the easy pose. The easy pose is quite similar to the render people. The standing pose and the fashion pose is quite similar to the render people. And another part is, I just call it a hard pose. The hard pose means the pose distribution of this dataset is quite different with the pose distributions in render people. So I test all the related works like PyFu, Pamia, icon, and the different modification of icon in this dataset. And the metrics includes like the chamfer distance and point to surface distance, and also the normal consistency.
So let's spend a second on what do these metrics evaluate. So the chamfer distance, you basically measure this is between two sets, right? So one set is your input, but this case the input is an RGB. So an RGB image.
No. The chamfer distance was defined between the reconstructed mesh and the ground truth mesh. So also both the chamfer distance and the point to surface distance, just to evaluate how close the reconstruction and the ground truth mesh are similar to each other.
Right. So because in these data sets you have a ground truth mesh, and you can compare to that. right? In
Yeah.
both directions, right?
Yeah, exactly.
And the other metric that you mentioned, the point to surface, it's just a one directional chamfer distance, right? So point to surface is from your output to the original ground truth mesh, and chamfer is that plus from the mesh to the output of the method.
Yeah, exactly. Right? Exactly. And the normal consistency was defined on, we just render the reconstruction and render the normal image from the different view of the reconstruction, and also do the same case on the ground truth mesh, and just compare the image difference. If we can perform better on the normal consistency, which means the details are better. Yeah, because they are the metrics is not consistent with each other. In some cases, the chamfer distance is better, but the normal consistency is not that good. The chamfer distance and the point to surface distance mainly focus on the to evaluate the similarity between the two mesh, especially the human pose. If the human pose is correct, the chamfer distance and the point to surface distance are pretty small. But the normal consistency mainly focus on the details on the mesh. So if the details are correct, the normal consistency will be smaller.
Mm-hmm. Yeah. Okay, so the chamfer distance and the point to surface basically quantify how good you are regarding to the general pose, and maybe a little bit on the mesh, but not too much on the details. And the normal consistency basically quantifies how good you are on the details, like the cresses and the clothes, the small details on the clothes, and all of those components.
Yeah, one for cross shift, one for geometry details.
And what did you find then?
There are several findings. First of all, we try to evaluate the Pamia with the ground truth simple body, and we also evaluate the icon with estimate or with the noise simple body, but with the refinement module. The refinement module means the iteratively refinement module. But the final results show that the icon with the refinement module performs better than the Pamia with ground truth simple body. So which means the refinement module was pretty good. So it can give us a very accurate human pose estimation. And another finding is that we try to combine the PyFu with icon. We also add a global encoder in icon. The input of the global encoder is the input RGB image and the closed normal, and to try to output some features which will fed into the implicit functions. But the performance decreased. So which means the local features is very important in icon. So the global encoder is not that necessary. We can just remove that.
That's a very interesting finding, right? Because most previous method used that global encoder, and it actually turns out that it's better to have all of those, use all the local features actually instead of global ones.
Yeah.
Which brings me to the question that all of this training data it's all synthetic, right? You have the renderers generating the RGB images, and like the background is very flat, and the meshes they're very nice and smooth, right? And you have all of the ground truth. How does this generalize to in the wild examples? What happens when you take an image not rendered, like from an actual photo?
That's a good question. First of all, the render people, if you look into the render people scans, is pretty high quality. And with all the wrinkle details, with perfect albedo texture. So at the beginning, we firstly try to generate the synthetic data, which is very realistic, photorealistic, to make sure it's similar to in the wild images. And on the other hand, during the inference, we just remove the background. We use some segmentation method. It's an open source tool set. It's very useful for our project, which name is RemoveBG, REMBG. And this package can remove the background for the images with the general background, not very complicated background. The RemoveBG can work pretty well. So we just use it to remove the background. This helps a lot for the final reconstruction results. Yeah.
What about attacking the problem from the other way, right? You try to remove the background to have it match the rendered images, but have you tried for the rendered images just to generate like a random background every time? Like just take an image from anywhere and put it
good question. And this is exactly what the PyFHD did.
Okay.
Perfect HD, they generate the random background using the MS Coco, and they train the network without any background remover. And but in there, if you look into the GitHub README, there's a sentence like, if you cannot get a good reconstruction, please use remove BG to remove the background. so which means for now, the implicit function-based method cannot work really well for all kinds of different backgrounds. So this is the reason why I just add these segmentations in our framework. I think it works well, and remove BG can give us a very clear foreground human person.
Is there any surprising outcome, something you didn't expect in the experiment that you stumbled upon?
Oh yeah, there's one. Because during the testing, we already talked about the quantitatively results, but for the qualitatively comparison, we just collect some images from the Pinterest website with challenging posts, and some of them are cartoons. They are not the realistic images; they are cartoons or caricature images. And we just test icon on these images, and it works well.
Oh, that's really surprising.
It's also amazing for me because I didn't expect that they can work. Icon can work well on these cartoon images. But I think the main reason why the icon can work on this image is because the current state-of-the-art post-estimation method can work on this part. So during my experiment, I find if the post-estimation totally failed, like the head is on the wrong directions, or there's a serious misalignment between the legs and the silhouettes, the final reconstruction is not reliable. So it's totally crashed. As long as the post-estimation is roughly aligned with the image, and then icon can firstly do the refinement to make a better pose, and then do the reconstruction from the input image. That works well.
Yeah, that's a really interesting find. Conclusions and future work. So how do you see the impact of the paper going forward, and what interesting project do you think still lie ahead?
First of all, I hope the more and more people can use icon to test on their images. And this is the reason why I released a Google Colab in our GitHub page. And so anyone can upload their images on that and to test their images. And as for the future works, I think there are several directions. First of all, we can improve the icon to, like we can do an icon plus to improve the details and the close details, and to make the reconstruction more stable. And it can generalize well on more challenging poses. And also there's a limitation for current version of the icon, which is if you run the code, you will find that the predict normal image is quite good with all the details, but the final reconstruction mesh is not that good. So there's a quality gap between the normal image and the geometry mesh.
Moving on to my favorite part of the podcast. What did reviewer 2 say? Please share your experience from the review process.
I can tell you the scores of this paper. During the review, there are 3 reviewers, and 2 reviewers give us a weak accept, and another reviewer give us a weak reject. But after rebuttal, we have 3 weak accept, or 2 weak accept, 1 borderline accept. The main reason why the reviewer 2 have give us the weak reject is because they feel that we need to use some simulated data. Like the simulated data means the render people are captured data. So the render people the people use the multi-view camera to capture the person, very fine details, but and the perfect albedo. But the reviewer 2 said we need to use some human mesh, which are simulated by the Blender. There are some such kind of data sets. But for the previous methods, all the previous methods, also including the icon, all use the capture data to generate the images. The reason is the simulated human mesh didn't have so much details. And also, most of them didn't provide the textures with fine details. The simulated human meshes with the textures are with limited colors, like all red t-shirts, all blue pants, So they didn't contain various different textures, but that is pretty necessary for our trainings. We want to our model can generalize well on the in the wild images, and the clothes in the wild are quite changing a lot.
Yeah, I can totally understand why they would ask that. Like, it's a naive question, right? So why not just use a lot of simulated data that you can generate as many as you want, and then you don't have the data scale or the number of examples problem. But fact is that if you generate synthetic data, it's just not reliable enough, right? The clothes are not fine detailed enough. You don't have the wrinkles. You don't have all those details. And even if you do have some of it, then the lighting effects are not great. And like the clothes are not, there aren't enough variations in this data to generalize, right? And this is what you want. You want to generalize to in the wild examples from any camera, anywhere.
Yeah, and also most of the synthetic data didn't have haircut and didn't have any shoes. They have some close wrinkles. Of course, they have some wrinkles, but it's a very close wrinkles. There is a domain gap between the synthetic data and the captured data. The captured data has very fine details. And also they have a second, they feel that we need to compare with ARC Plus, which is two related works from Facebook. And actually, after the submissions, we just give all the test images to the Facebook Reality Lab, and they just give us the reconstruction mesh. So we just add this image into the rebuttal document. And but the reason why we didn't compare it before the submission is because they didn't release any code. So we of course we can reproduce their methods, but it's a little hard, and due to the time limitations, we didn't finish that. So after the submission, we just send the images to their researchers, and they give us the reconstruction method. And thanks for their help.
Yeah, it's always hard when you're asked to compare to a method that didn't release the code. It's very nice that they actually got your data and were able to run it and send it back so you can report a comparison. But yeah, it's always like, I think one of the things that made the field the way it is today, that it's going forward so fast, is the fact that people are publishing their code and making it available for everyone, so you can A, learn from it, but B, have like a fair comparison to it, and you can actually make significant progress.
Yeah. I just released the code and also with the Google Colab, so everyone can test your image on our Google Colab. And also, for now, the release code only contains the test part. But we will release the training code and also the data processing code in the near future. And also, Icon reproduce the PyFu and the Pamia in the same framework. So in the future, if you want to like train your dataset on the PyFu, Pamia, and Icon, and to report the final evaluation numbers, you can just use the Icon, because Icon contains all these three methods in the same framework.
Oh, this is awesome. Like, you're awesome for doing this. This is one of the things that, it's not trivial. Like, writing good code is hard. Cleaning it up is hard. Making it publicly available takes time and effort to maintain it. And the fact that you did that and did this Google Colab that anybody can just take their images and put it on there and test it and play with it, I think it's super important. It's one of those awesome things that keep pushing the field forward. So kudos on that.
Thank you. And also the reason I want to why I reproduce them is the PyFu and the Pamia, all kinds of different, they didn't release their code, but they use different dataset, and they use different training strategy. So there are a lot of difference in their methods. So for a fair comparison, I just merged them in my framework. So for now, the only difference is the method or the network configurations. All the other parts, like data loader, the training strategy, and the training dataset, are all the same. So in this way, we can see that we make a fair comparison with all these methods. And also, I will release all this code so people can do the same in the future, because I think different labs have different datasets. So they want to evaluate on their datasets.
I would say this is another important contribution of this paper, that you created this standardization of the problem. I mean, I know it a lot from the field of 3D point cloud processing and classification, that in the beginning, the field was like a mess. Everybody would take whatever data set, do their own augmentations, use whatever, like it was a mess. Everybody did something else. And then at some point, everybody kind of converged into this one standardized approach. And it seems like Icon did that for this problem. And I think that's a huge contribution to the field as well.
Oh, thank you.
At least for the community. All right, then I think we have everything covered. Thank you very much for agreeing to be a part of this podcast. And until next time, let your papers do the talking. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.